We are so back, y'all. Hope you enjoyed that intro. Shout out to my friends Caliber and TCB for the music. That was just a quick and dirty thing I pulled from existing content and lighting programming, but there's a lot more where that came from. As you can probably guess, I've been busy building technology to power this channel in the long term since the second half of 2021, with several prototypes along the way. Long story short, it amounted up to 2.5 jobs between video, my own visualizer dev, and freelance visualizer dev that actually paid the bills a while. Eventually I needed to cut back to just my own visualizer dev for the sake of having my own mature, reusable technology which wasn't happening while split 3 directions. That work is now majority complete and has been refined for around 3 months already after a couple years or so of post-prototype production between in-person shows as well as some burnout last spring. So where are we now, and what's next? We are currently around 6,000 lines of C++ and HLSL shaders later into the current repo since its creation in late 2022, over around the past 18 months, prior to which were isolated system prototypes. I'm now aiming for another 6 months of polish, or ideally less, now developed out in the open with updates on YouTube and on stream moving forward. Also, I'm a furry VTuber now. The channel content and goal will remain the same as ever, however video production will be different and better now that I'm giving it the same attention and treatment that I give to live event production. A VTuber debut will happen later today, Thursday, May 2nd, multi-streamed on Twitch and YouTube, shortly after this video premieres. See the pinned comment for specifics. After this debut, the same VTuber setup will also be used for future VOD content. Most importantly, an unstable preview build will be due out on Patreon and or Ko-Fi during the month of May. Seeing as this is a soft relaunch, more details will follow when the time comes. Further, to hold myself to that target, the tasks slated to be done on stream are specifically those which are directly related to shipping that preview build, having now built internal demos to expose and fix the worst of the problems, from which it was too incomplete and immature to debut prior. So, what is T3D and what is it about? What is it? T3D is first and foremost a lighting visualization framework to simplify the tedium of building fixtures at scale, taking the form of an Unreal plugin. However, it also has potential to later subsume my previous VJ tooling schemes as well. I may later be inclined to describe it as simply a lighting or stage visualizer, after it has a sufficient fixture library attached as well. Also, building stage plot tools in Unreal would also be possible, however, is extremely cursed and is not planned in the initial scope. This is, however, on the table if the community demands and funds it enough. So, project philosophy. T3D aims to be easy to work with and democratize lighting visualization as much as is reasonable within the bounds of accessible Unreal tools, and within the constraints of financial viability of open source adjacent projects, which is already well established to be an uphill battle. Further, T3D aims to be scalable on multiple axes. Firstly, building technology which facilitates wide fixture variety, for the best chance of long-term library completeness. As an example, first, think of a base abstraction where any fixture is a collection of one or more DMX attributes, applying to one or more pixels. Next, think of all the edge case designs which will immediately break that, such as strobes with mixed RGB pixels and pure white pixels, or the meme of a light that is the Chauvet Gigbar series. With some 20,000 models of fixtures out there, we want abstractions which can cover as much of that range as possible. The second axis then, performance. While library extensibility has upfront complexity and performance cost, the intention has always been for small stages to be viable on Quest 2, with room to go bigger and better on PC, with a mind towards building core technology as such. I'm also thinking of Quest 2, in a way, as a proxy for performance on iGPU gaming handhelds and similar laptops. Thirdly, a stretch goal of interoperability, optionally supporting various lighting and render platforms, and broadly enabled the sharing of assets wherever possible to do so. So, how does this all work? As of now, T3D will be comprised of 2 Unreal plugins, starting with the T3D Library plugin. Approaching a full release, there will be a fully open T3D Library content plugin released on tentatively GitHub, which will house the fixture library content, such as blueprint prefabs, meshes, fixture profiles, and other fixture assets. While I'll have some details to figure out at that time, this would be a good opportunity for audience participation once we get that far. Then second, the T3D Core plugin. The T3D Library plugin will depend on a C++ and shader plugin called T3D Core, which will tentatively release as free binaries for relevant Unreal versions come full release, with source code available via Patreon and/or Ko-Fi to balance the tension between openness and funding. Further, this has room to change depending how interest goes, with an ultimate preference to be fully open, if and or when it should be financially viable to do so. This, however, is not a decision to be made now and is not made lightly. As before, the T3D Core plugin remains based on the standard Unreal DMX plugin. Other DMX platforms or alternate protocol subsystems, such as OSC, are being considered post-release. Finally, the Core plugin is itself comprised of 2 Unreal modules. Firstly, the T3D Core module is the default plugin module and contains all of the fixture logic and DMX features, including support for most multi-pixel configurations. Secondly, the T3D Shaders module, which handles the custom shader passes for my integrated procedural beams, using a mix of compute shaders and pixel shaders on Shader Model 4 or newer platforms. These will be my default beam tech art for the foreseeable future. More detail on this when we're actually seeing them. Okay, enough preamble. You want to see more. What you'll see is essentially the complete, robust, and eventually easy-to-use fixture framework I intended to build from the beginning. The goal of which is users should not need to write any code or nodes and can simply build and configure fixtures fully in the blueprint editor via properties, not unlike fixture editors and lighting consoles. More specifically, what you'll see and have seen in the opening and new website is a demanding work-in-progress test scene based on a real-world stage I programmed and co-designed. It comprises just over 750 DMX pixels with multi-pixel support, and very nasty transparency overdraw without optimizations or with all fixtures turned on. Unlike virtual scenes, real-world stages aren't designed with performance in mind, so this is a useful test case to push the limits, optimize, and subsequently push farther. While incomplete, the features used in this stage represent the overall majority of features needed. The vast majority of the features used are operational enough to be demoable, however still need further tuning, which applies across the board. Mostly that which still needs implementing outright are theatrical beam shapers and other color engine variations, but those are intended for inclusion in the version 1.0 scope. The inclusion of further beam shapers, however, has been extensively planned for in the procedural beam system, as already used by Gobo. So, moving along, I've programmed this show in MA3, so we'll be referring between that and the Unreal view. There's already some great MA3 content out there, but if you want me to do some, be sure to let me know in the comments now that I'll actually have a bit of time to read them. Okay, here we are. We got a viz. We got a console. We got both. So, fixtures then. We have ADJ 12p hex bars, Megalight bright stripe bars, Chave DJ color band PixM USB tilt bars, which do in fact tilt, we have ADJ VisiWash Z19 moving wash, which also, that one, which also does exactly what you would expect. And then we've got ADJ Focus Spot 4Z moving spots. So, attributes that these all have. Of course, you've just seen dimmer, they all do dimmer. That's expected. All of them, except the stripes, have physical shutter channels, and those work. However, in my show, I've just got virtualized dimmer phaser effects in MA3 just for ease and for compatibility with fixtures like the bright stripes, which do not have their own dedicated shutter. So, oh yeah, strobe warning. So there's that. There's the stripes. strobing even though they shouldn't be able to. There's the PixMs, there's the Z19s, and there's the 4Zs. I have pretty much the same implementation for the shutter channels. It's just this show file is from a real stage build, so it's sort of programmed for that, with that in mind. So that's shutter. Now, then, color effects. Starting with color mixing. So that's basically everything except the 4Z. And as you can see, they all do rainbows, and everything that supports multi-pixel, or has multiple pixels, supports multi-pixel. That would be the PixMs and the Z19s. It's probably easier to see if I master them down more, or not really. Nonetheless, we got the multi-pixel support going. Specifically on the Z19s, they support their, if I grab them in, I don't know, red, that kind of highlights it better, that the different zones of the Z19s are correctly in there, and you can also kind of see it with a chase. So back to open, take everything back to white, and then we have the 4Zs. Right, the 4Zs are different. They have a color wheel instead. So we accommodate that too. This looks a little janky because the color wheels and gobo wheels in particular need better calibration, but they're in there, they're tuned. Once they're tuned, they'll be in pretty good shape. So, I mean, pretty much that's color. Okay, so then besides that, the last thing is, at least for now, is the 4Zs also have their gobos, as mentioned. So we can pull these out to wait a moment and throw in a gobo, and yeah, they got a gobo, and I can throw a color split that one of the colors happens to land on right now, out of my standard color palette or whatever. It just happened to land on a color split at the moment. So if we just rock that, I can bring these up, and I can even, I can kind of point them at the truss, brighten them up a bit, and then I can throw them on a pan sign, and you can kind of see the multiple colors sweeping over the truss, because the light components themselves, long story short, that feature's a pain in the ass. Light components can only be one color, so it's a bit of a hack, but I have made the hack, and we have split color support. So if I pull them still, and then I open the gobo, maybe that's a little easier to see, just barely. Anyway, yeah, so split color is good. And then, that's the initial set of attributes. I have, of course, Prism in my show file. I haven't done Prism yet. As I believe I said already, basically I need to do Prism, I need to do beam shapers, and I need to do the more complicated color mixing setups beyond RGBW. I believe the industry is now out to red, green, blue, amber, lime, white UV is the new hotness. So that'll come in time. That's just kind of tedious housekeeping work to add the more color variations, but it's easy enough to do and get done at some point here. So then that kind of concludes the DMX attributes that are involved here. Oh, right, I forgot zoom. So yes, we also have zoom on both of these. So if we pull these up and pull everything to white again, both the Z19s and the 4Zs both support zoom, and that works as you'd expect. So let's just double check here. Dimmer, shutter, color mix, color wheel, position, zoom, and gobo. Those are all in, those are all working. And again, notably with the 4Zs, those use my own procedural beams using a technique which the industry has eventually come to refer to as a computational solid geometry. That's just fancy words for saying you take some data set or whatever and you make a mesh out of it. It's a particular class of algorithms that these details aren't too important, but essentially I have reframed the problem of beam rendering compared to traditional ray marching, which can be heavy. This also is heavy as it currently is configured, but ray marching is essentially very similar to ray tracing in that it is, from the camera perspective, it's doing essentially a for loop per pixel, and it's not cheap. The debug view on this also is not cheap, especially when I do what I just did in terms of framing. But nonetheless, this at least is badness that shows up in your debug views. Ray marching may not always, just due to the nature of HLSL, custom material nodes, and running one or even two nested for loops in a pixel shader, per pixel, which, and in certain, depending on the quality of the ray marching that they're aiming for. Ray marching can be cheaper or whatever. Okay. You know what? This is good, but cut this entire ramble. Holy shit. Like, everything from ray marching. Goddamn. Let's just back off a little bit. I will let this run like this for B-roll, technically, in terms of the video side. Okay, so let's just go back to here. Okay, so we are going to need to edit a little bit. So let's pull these center, let's pull these open, let's pull these closed. Okay, so procedural beams. Yeah, these are using my procedural beam technique, which uses a family of algorithms the industry has come to refer to as computational solid geometry. Essentially, it's a way of generating procedural meshes from another data set. For the technically inclined, it's based on signed distance fields, for which I'm encoding all of the elements of the essentially light engine simulation in terms of everything that shapes the beam is encoded and rendered as a signed distance field. Such as gobos, iris, framing shutters, etc., all of that runs as a light engine pixel shader, and then that feeds a compute shader, which generates the geometry. So with that, we have the benefit of essentially decoupling the beam rendering from the camera perspective, which notably ray-marched volumetric fog, which is the industry standard, is very good, but it is expensive. It is very similar to ray tracing. and can use as much as 1, if not 2, for loops per pixel. And that is rough in a way which doesn't necessarily show in your debug metrics. This, in its current configuration, is also pretty rough, but it does at least, all the badness does at least show up, because it's simply just fairly basic materials, just overdrawing a hell of a lot. There's optimization that can be done, and to a certain extent has been done, although I'm not sure if it's in this build or maybe I broke it, I don't know, but nonetheless, there's optimizations that you can do, and I have been playing with. But at the end of the day, lighting viz is kind of inherently expensive, but I essentially devised my own technique. I sort of knew of some of the algorithms. I didn't necessarily know the fancy name for the overall computational solid geometry space. But I just kind of noticed SDFs, noticed that you could, make a mesh from them, did the research online or whatever to, figure out the things, and then eventually, put the pieces together and, essentially rediscovered. Not at all the first person to do this. Maybe the first person to do this in kind of the lighting viz space. I don't know. I don't really care. But wow, this ramble is horrible. This ramble also is horrible, but maybe it's salvageable. Camera perspective like this is highly valuable in that if decoupling the beam rendering from the camera perspective is highly valuable in that in doing so, you make the problem a cacheable one, which is very handy in that means you can scale all the way down to devices such as Quest 2, which do not have robust support for compute shaders, at least in Unreal. So with that, especially since it's not going to work for every kind of fixture in every configuration, when you're caching, you're not going to be able to do stacked gobo wheels for fixtures that have more than one, but these only have one. These only have one attribute that can shape the beam, and that is the gobo wheel. And because of that, with a single byte 8-bit DMX channel controlling the position, that means there are only at most 256 possible states, which that is manageable, that we can deal with. And so even though Unreal doesn't support compute shaders well on Quest, at least as of 4.2.7, maybe it gets better in the latest builds, but in the versions that I tested, this was a solution that worked, and although I have not tested the fixtures on device, I have tested the core technology on the device, and it works beautifully, and it is very immersive. I have some clips. Maybe I'll insert them in the B-roll here in the edit. It is very good, and it is wonderfully immersive, is, I guess, the best way I can phrase it. So there are certainly trade-offs. I need to, since I don't at least know of anyone else who's done it this way, and certainly there's, now that I'm on the other side, I've to a certain extent discovered there's maybe good reasons why people haven't, but nonetheless, I basically need to find the crossover point of when to use this versus when to use ray-marched beams. And ultimately, it is a comprehensive solution. My plugin is up to 6,000 lines at this point. So that complexity is somewhere, and that complexity, a lot of it, lies in essentially a unified beam, not component, but a DMX pixel child actor, which houses, a beam mesh that's, correctly set up for all this, with all the scripting for that, a lens mesh, and all the things just kind of integrating into one thing that you just attach in the blueprint editor, and it just does the thing. And in that regard, it should be easy to use. We'll see how it all pans out. Yeah, so I think we've got some good stuff here. This is currently in 427, as I think I said. As for UE5, we'll get to that. I will have to deal with the migration to large world coordinates. With that, I will probably need to swap to a different procedural mesh component, and with that, probably a different mesh format, but nonetheless, we'll get there. And then, yeah, that's, I think, pretty much the situation with the beams. I have prototyped some of my own ray-marched volumetrics. Ultimately, I absolutely want to support both. So I've been, I did the core technology to be able to scale down first. And then, because in terms of scaling down, yes, the overdraw on desktop when this high quality mode is really bad. But by simply just reducing the amount of voxels that we're meshing the beam into, it will miss more of the higher frequency details, kind of like in these kind of nature pattern gobos or whatever. It'll miss those details, but it will, kind of linearly scale quality rather than, oh, you can't do ray marching, ergo, you just can't use this DMX attribute. It's a little more graceful in that respect. So, in light of that, I'll also do the ray-marched volumetrics for these higher quality situations. Maybe it'll perform better here. I'll have to find an experiment where the crossover point is to sort of when is best to use which. But yeah, we'll get to that. So with that, I think that should largely conclude this portion of the live demo. Next will be loading up a blueprint editor to tear a couple of these apart so we can roughly see how they go together. Very, very much work in progress, but we'll get there. Yeah, it's about time you finally see this stuff. So here we are. Let's see roughly how these are put together at a high level. Written docs and nicer video reference will come towards release when I'm finished changing and cleaning up these data structures of old experimental craft. For now, though, let's get this thing open. And we have, for components, we have a scene root component, which is pretty standard. The mesh for our base, which actually is empty on this one. A yoke mesh, a head mesh, a spring arm for any kind of zoom functionality, kind of as standard. And then we have child actor components, which comprise all of our pixels. And then those in the child actor template have all of the configuration of the lens material and the stuff that drives the procedural beams and all that fun stuff. Get one of these configured and you can pretty much copy paste easily enough. Obviously none of this is final and a lot of this is going to be adjusted and cleaned up and so on, but functionally it's just you add a pixel component or a child actor component and then set that to be a stage pixel, and then you can kind of have things nicely all contained in one unified actor to where it kind of simplifies all of the technical art setup, especially on the runtime side. So then, of course, we've got a standard Unreal DMX component. We can look at other DMX or other protocol subsystems post-release. And then, yeah, we got dimmer, tilt, shutter, color mix, and right now there's a gobo wheel component on here. It might not need, obviously it doesn't fit. It's not a feature that it has. I think I might have slapped that on there just to bully the procedural meshes to play nice at some point. of course, reevaluate that actually needs to be there. Ultimately, it should go away is what should happen. But nonetheless, that's pretty simple there. And then, again, a lot of this also needs some cleaning up, but we have essentially a data structure here where for each, we have a slot for each personality, or each like DMX mode effectively. And then with that, we basically have definitions for each of our components per DMX instance, which is kind of my phrasing for referring to a DMX logical pixel. Like we have our physical pixels here, but then we also in the code have logical pixels, which are technically separate. So for dealing with that, we have this. So we have basically our root instance. Don't worry too much about this. The important thing here is tilt. And then, yeah, basically we have our tilt. Some of these properties definitely will go away to clean this up and look nicer and be easier to deal with. But essentially, yeah, we essentially define in here how each DMX attribute relates to the individual instances and multi-instances. So like you have this tech art is like kind of the root pixel 0, instance 0 tech art, and then you have the other pixels up here. So in terms of defining how all of our DMX features interact with that, a lot of that configuration is generated at runtime, but in order for it to know what it needs to do with that, we have this stuff in here. Notably, we have like the initial just the one, and then we have in the second entry the one where it can have multiple of itself. So you could like manually make 10 more slots, so you have a total of 11 elements in DMX template feature instances, but in this case I just made it ranged, so we can just say we have a root instance and then all of our pixels, we add just one more, and we say, hey, this starts at 1 and it goes for 10 pixels, and we have all of our per pixel features. So that includes color mix, dimmer, which actually, just to run through, color mix, dimmer, shutter, those are all native features. We also have zoom on here, which is not normally needed, but in this case, depending on how you do the tech art, you can either like tell it to initialize a certain way in here, or I think since I've made this, I've switched to just like setting like zoom properties just statically in material instances is kind of a better way to do it. But nonetheless, just each of these just defines how these should all interact. However, also, I should note, this serves a second purpose. You see this is called DMX feature instance element blend groups. That is because I've also kind of snuck a compositor in here, which allows us to say, hey, for each of our individual color pixels, which come in as, like the dimmer for each pixels comes in as color data, we also want to multiply this with our root dimmer. Matrix data source is either standard or matrix, so we have the standard root pixel. So we take our standard root dimmer, our master dimmer effectively, if you like that terminology, and we multiply that up against our per pixel matrix color, so that we can get all of those behaving nicely. These are things that you need in a more robust fixture editor that you might have to special case. I'm trying to eliminate as much as that as possible. Certainly, if you just unfold all of this, it can be quite daunting, but as I clear out some of the old unused parameters and so on and get better documentation out, for which this is kind of only just the start, It should be interesting and hopefully useful to people, fingers crossed. So that's the PixM, which is a little more complicated. Then we can also come out here to here and grab our par as well. So this is a very similar setup. It's pretty much identical, just it has no base mesh, no yoke mesh, just a head mesh because it's static. It does have the standard spring arm for kind of zoom stuff, whatever. And then there's just one pixel. So that has the lens mesh here with like a static mesh assigned, and then lens material, all the stuff. Some tick boxes for whether it throws light or not, and so on. And then we just have standard dimmer, shutter, and color, which is all it supports. And again, this is in here. Probably it ought to go away at some point. Don't worry too much about this. And then, yeah, like when I was mentioning the Go's being not particularly well calibrated, that's because their attribute definitions begin and end with this at the moment on the 4Z. So this will go away. That should get a data table upgrade in due course. And then, yeah. So there's a lot yet to do, but there is a hell of a lot that's been done. Like I've been saying, 6,000 lines and like just even, oof. So yeah, this is pretty hefty. Yeah, that for source code, that's getting pretty decently high up there. Ryder said 6,000 non-empty lines of source code, give or take, in the whole project. So there's a lot going on, but when you consider that the procedural beams are underpinned by custom render passes in Unreal, actually, I think there's a couple different pixel shaders now, as well as a compute shader. Ultimately, it all adds up. So I think that also should do it for this portion as well. Thank you for watching. This is going to be a pretty meaty end screen. Stick around for that if you want to. Otherwise, you've kind of seen the cool stuff. And if visually this wasn't all that cool, we'll be doing plenty more on stream. So see you on the streams, and if you want to stick around for the end card. So, thanks for watching to the end if you did. We're only just getting started, but this year the concept in my head from during COVID is now being fully realized. For those interested in seeing more, videos will come roughly monthly when there are relevant updates. However, for now, emphasis will be on streaming in an effort of getting this thing to the finish line. To reiterate, you can catch my VTuber debut on stream shortly after this video is published, and a full stream schedule will be found on my Twitch page once it's complete. Lastly, with updates and announcements essentially out of the way, now for some important housekeeping. For anyone who's been around the channel for a while, this part's for you. So firstly here, I'll admit we had a false start. However well-intentioned, it's been tough balancing all the engineering for this project, with the engineering for clients wanting similar stuff from me, with the responsibilities of live shows from time to time, while keeping up with the effort required to do video content proper justice, which I simply haven't, while also supporting the existing community and supporters well before the core engineering was actually done, which was essentially the core work desired from subscribers, patrons, and freelance clients alike, if the original vision was ever to become a reality. So wherein things have been suboptimal, I want to make that right. That's why I had to get the core engineering done first, which I knew would suck for 2 to 3 years, but now we're through it, and I can better balance attention between ongoing development, video content, and community interaction. So with that, I'd like to personally thank all prior patrons. This video marks effectively a relaunch of everything, so all tiers are not yet, but will be revised, with options reevaluated between Patreon and Ko-Fi. If you want in on the preview builds, for now, simply wait for an announcement of the preview release and upcoming details of where to find it over the coming month or so. Anyway, as thanks for bearing with me, last year while there was light at the end of the tunnel, but it was very much still distant amid increasing burnout, members of the Patron Discord will know I gave them a role for permanent access to the release channel, so long as they stick around in there. Paying or not, special for them for putting up with me, prior to this thing manifesting for real. It bears repeating, I'm certainly perfectionist as hell, so with all the trials along the way, it's definitely been rough, but I nonetheless appreciate all the support to date, even if I haven't always been visible and been too deep in the engineering weeds to have headspace to make videos. Seriously, thanks to any and all who helped in any capacity along the way. Let's get this thing going for real this year. Regarding the backlog, firstly, I especially want to shout out Jimmy Music for sticking around through the slog and being incredibly helpful along the way. While I've essentially tackled this project solo to date, he's been a great springboard and even offered me unprompted to help with the logo design, starting from the name provided and iterating into a logo which I think came out great, and which I've since tweaked just slightly and subsequently authored a full branding and stream graphics package around. From here, on with a list of everyone prior, which will keep in the end card for the foreseeable future. You're still here?